I can't hear her. I'm muted. Wait.
Sorry.
Hello?
CyberSec.
What happened? What?
The CyberSec room is present.
What, you put, they jumped on her on the TV?
Oh, we worked on it, but my computer kind of crapped out. I'm joining on my phone right now.
Okay, use somebody else's computer.
Larry said I got you. He won't be here in a few minutes.
Zoom is garbage.
Zoom is garbage.
Correct.
I should just use Discord. Again.
Yeah, we should have.
I'm surprised you didn't.
Oh, is the owl working? No.
Oh my god.
Why is it blurry?
It's blurry.
Oh, here we go. Now it's working. Okay.
Sorry, I decided to use Zoom. I will never do this again. So I decided to use Zoom because I thought if no one was going to show up in class, then I wouldn't make Leon go to class. And so if I wanted to record it, then I needed to use Zoom. But
Well, I'm here anyways.
yeah, so it's going to be on 360 no matter what. Whoa, the echo.
Let me see this one. Alright, so it's not doing it.
Nice.
Why is this not working? Laptop.
COVID is garbage.
Bro, what do I do?
Have you tried plugging it in?
Oh, really? Like,
Turning it off and turning it back on.
there we go.
Oh, it is plugging in. It's nice.
Oh. Okay. Remove that. Okay.
Oh, that's
Oh,
the best part.
I gotta post the attendance post too. What's the attendance post?
He's just going to stream this meeting.
Yes. 14. Alright, class already started, guys. So, here we go.
Hello and welcome. Today we will be discussing yet another heap allocator. So I'm gonna share my slides and we'll get it going.
Petition.
And
Send request. Right.
there, it's gonna ask for one. Yeah, it is. All right, awesome.
Recording in progress.
Now here's the question. If I switch this into full screen mode, is it going to screw up Zoom or is it actually going to share? Is it actually showing the slides?
I can see it. It's sharing, we can see.
All right, perfect. All right, so the last two homeworks, which I'm going to post right after this class, are both going to be using JEmalloc. They're statically linked in. You're going to get the source code. We went over that source code briefly, quickly. Last class, we'll probably go over pieces of it several more times to help you out. This class, I want to talk about how these more modern allocators work and why they work the way they do and why you still need to kind of understand how they work, despite the fact that you're not attacking these allocators directly. And so what we're going to cover next class is kind of that blind heap manipulation. Now the homeworks are not blind manipulation. I have it actually printing out all of the pointers for you so you can look at what it's doing and understand the effect of what you are doing on the allocator. In normal real life, this is not the case. You're doing it blind, basically. So There are ways that you can use the fact that it's not blind to your advantage to solve these problems. I would suggest you don't do that, and I'll talk more about exactly what that means when we talk about manipulation in the next class. And part of the skill that I want you to pick up that I'm not going to be enforcing here is that the homework examples don't have background allocations occurring, and in real life they would. So you could take advantage of that fact to kind of cheat a little bit, but when you get to the real world, it's not going to help you out. So the reason that I don't have that in there is because I don't want to add a probabilistic function to this homework so that grade scope becomes like, how high probability did you make your homework? In real life, you're going to want to make it as high probability as possible, but I don't want to deal with that in homework, and probably you don't either. Nobody wants to finish their homework with an 80% probability of scoring correct.
377.
All right, so what is JEMALIC? First off, I had meant to have a slide in here that has, what's his name, Jason Evans' picture. It's not nearly as fun as Doug Lee's picture. He just looks like a normal white dude, so you pretend you're looking at one right now. But JEMALIC is basically the progenitor of all of the metadata consolidated allocators. So it was built to replace the old school BSD malloc, which was PHK malloc. It was built for FreeBSD, and the whole goal in writing it for FreeBSD was efficiency. And this is like a different type of efficiency than we were looking at with Doug Lee's malloc. And in Doug Lee's malloc, we were trying to be efficient in memory usage. So we did a lot of consolidation and chunk cutting, and that used more processing power, right? This allocator is focusing on a couple specific optimizations, and they're all speed optimizations in the mind of this developer. And so we're looking at, that's a typo, not multiprocessor, but multiprocessor scalability, and then that low fragmentation. And the reason that we're looking for those things is we don't want to tax the processor. We want to be able to allocate very quickly without having to do a bunch of context swaps for the processor. And further, there is like some cache line optimization that is occurring here. And I'll talk about more about what kind of cache line optimization means and how this accomplishes it as we get kind of into the flow of it. So you can imagine that all the stuff that I say about JEMALIC here at the high level, the goals and the structure, those also apply to the Windows low fragmentation heap. The particulars of the particulars of JEMALIC will not apply to low fragmentation heap, but you won't really need to know those for manipulation purposes, right? So everything you learn here, you can assume it applies for low fragmentation heap when you're talking about exploitation. So where do we find this JEMALIC? Well, so you guys looking at Linux have expected to have ptmalloc everywhere, right? On the little programs we're running, that's what glibc compiles in, but almost every large program you interact with is using a heap of this style nowadays. So everything in Android, it's the only allocator in Android. Most things in Windows after a certain threshold are using this style. All web browsers, every Electron application. I don't know if Firefox has switched over to JEMALIC in particular, but it was using its own kind of arena heap allocator that looks very much like JEMALIC. Chrome, everything like that. All of those things where you're allocating a lot frequently, and you don't want to be wasting processor on it. They're all using a heap that looks like this. To be specific with the Windows stuff, Windows is looking at certain thresholds of allocation in a program, and it's once a program reaches a certain threshold in terms of size allocations over a certain period of time, it switches over to low fragmentation heap. And so if you're going to exploit a Windows program remotely, you have no idea what heap it's using, but you do know what algorithm it's using to decide when to switch to low fragmentation heap. And so your goal is basically force it to switch to low fragmentation heap so that you know what heap it's using, and then go from there. You'll never try to attack remotely the other heap application. Yeah, did I lose my?
You're not screen sharing the presentation.
Say what?
You're not screen sharing the presentation because it doesn't change.
That's what I asked.
Oh. No,
You guys are like, oh, I can see the slides.
No, okay, we thought you just meant like you can.
I can see the slides, yeah.
No, but like
Wait,
you
is my
see the
face-
slides, but on the first slide, I assume she keeps referencing stuff on slides, but hasn't moved.
Oh, I thought she was just like talking.
That's what I thought.
I'm talking about the slide that's up should be what's JE Malloc. Can you see what I'm switching right now?
No, we don't.
All we see is the first slide.
We just see the titles thing in the.
Awful. Let me just, all right, I'm just going to share the desktop capture right now.
There we go.
Okay, that's what we wanted, yeah.
All right, so this is the slide that should have been up the whole time that I was just rambling. It has a couple bullet points that cover the stuff I'm rambling about. Thank you for the heads up. Of course, now I have no clock, but that's fine. All right, so what is the main difference that we're looking at here between JE Malloc and DL Malloc? The main difference is that is where the metadata is stored, how much metadata is stored, and how we think about chunks. For DL Malloc, you just did 2 days of lab where you are attacking the metadata of the allocator, you're creating fake chunks, you're doing all that fun stuff, because that metadata is in the same place as the data, right? JE Malloc makes a differentiation between the data plane and the control plane, as we call it. And the data plane is where your program puts its data, and the control plane is where the allocator keeps track of that stuff. And those are in different pages, and there are non-adjacent pages, and there are generally guard pages between them. So you don't bother to attack the metadata in a JE Malloc situation. It is abstracted from your data plane. But that's actually good for us as we see looking at kind of newer implementations of PT Malloc, which is the current implementation of DL Malloc. There are a lot of pieces of validation in there to make sure the metadata still makes sense, and so you can be caught manipulating things. Even if you're not manipulating you don't mean to manipulate the control data, you can be caught doing that. Now, that's not necessarily a big problem, as we will see in coming classes when we look at manipulation and what's necessary for that. But that was one of the problems that hackers had at the time when they're looking at dealing with this stuff. It's like, oh, I can no longer perform my boilerplate solution to the problems. I have to be specific to the program, right? So let's talk about the top level structures and how the program kind of looks at the heap in JE Malloc. So DL Malloc has basically one basic arena. That's the one heap that everything comes from and goes to. When you call alloc or free, it all comes from one big pile of garbage, and it all goes back there. And JE Malloc, there are many different separate heaps. And basically what you do is you say, in the default configuration, how many cores does this computer have? Okay, say it's got 4 cores. I'm going to make 16 different heaps, and I'm going to round robin as threads come into existence all round robin between those heaps. So each thread basically has its own heap that it's allocating from now. Threads can still share memory between one another, but anytime your thread allocates, in general, it's going to allocate from its own heap. And so somebody else may free from your heap, but that's pretty rare, right? Someone else may access from your heap. That's fine. That doesn't actually make any change to the heap metadata. So the reason that we're doing this is a couple reasons. The first is that we don't want to have to lock and block on the heap structures when a thread allocates or frees, right? And that's going to, if we only have one heap, every single thread is going to be talking to that same heap metadata. And as we learned kind of from reentrancy issues earlier, that is a great way for corruption to occur when multiple threads are working on the same complex data structure. So we'd have to lock it. In this case, if every thread is allocating from its own arena, generally the overlap of locks is not going to be there, right? So that number of 4 per core is tailorable, but J.E. Malik was actually written with a great deal of academic precision. There was a lot of testing performed and a lot of different both live programs and testing heap test protocols to figure out, what is most often most efficient at that point in time. And so over time, as you get more cores or more RAM, those numbers change, and they're tailorable from a file within Etsy on FreeBSD or wherever else you've got J.E. Malik running. They're very tailorable. And so Chrome probably is using different numbers than Android, et cetera. Within each of those arenas, there are multiple runs. And a run is a series of M-mapped pages from which we may do allocations. So like when we looked at DL Malik, you had one contiguous chunk of space, one contiguous set of memory pages that DL Malik would pull from and write back to, right? And it all goes back to that one place, it all comes from there. Each arena, each heap in J.E. Malik has multiple sets of those. And they are split by chunk sizes. So this is like a totally new way of getting memory for the process, okay? So because I'm terrible with slides, I've already said all of these things. Yeah, we've got those multiple arenas for several good processor speed reasons, right? We're looking to save processor speed, and often with J.E. Malik, we're trading memory space and unused memory for processor speed. The reason that we call this low fragmentation is not because we want to save memory overhead. It's because we don't want to consolidate and split chunks. That's computationally expensive. It takes time. It means that you're using less memory, but you're using more processing power. And here we're going to make the other trade-off, right? We're going to say we're going to spend more memory overhead in order to have less processor churn every time we allocate or free. These runs are per chunk size. So every power of 2 chunk size gets its own run, and we never split and we never consolidate. So if you want something, you basically take the number you're asking for, you round up to the next power of 2, and you pull a chunk out of that list, and that's that. And there's a bitmap that's saying which of the chunks in this run are in use and which are free, and that's basically it. So no matter what, it's always constant time to pull out a chunk and hand it over, right? Because every run is going to have its own size. Now that means that there's a lot of overhead here because we're going to map a whole bunch of runs. The first time we get a request for a chunk of a given size, we map a whole run for it. And that run's going to be of a given size that's tailorable, and then it'll be doubled as it's full up. Okay. So let's see, I think I have kind of half of my slides are covered by my Zoom nonsense, which is a problem. No, that's not what I want. No. That's what I want. There we go. Does anybody have any questions so far about, why this thing exists and what it's doing?
Yeah, so I just kind of want a clarification. So when we're requesting a chunk of memory, is that request kind of being concurrently processed and then it returns the first chunk that's available?
What do you mean by concurrently processed?
So, like you said, the allocate. So you request a chunk, and you said something about having multiple threads. So on each thread, it's trying to find a chunk, and then the first thread that returns the chunk is the chunk that's used to allocate the stuff you want to.
Oh, no. Okay, so the allocator does not have multiple threads. Your program has multiple threads, and for each of your program's threads, it has its own heap.
Okay. I see.
And so that thread itself gets its own chunk. It's not like multiple threads are running through a single heap to find a chunk to get it back to your thread. Your thread has its own heap with its own chunks, and it just gets the next one. And
Okay.
So there's no, doesn't need to lock necessarily to do that, right?
Okay. So each thread basically has its own heap and does its allocation on each thread, right?
Yep. Yeah, it does its own allocation. It calls into the libc allocator to do the work the same way that dlmalloc does, but it's got its own set of mem-mapped pages to pull those chunks from.
Okay.
Anybody else? I wish I had a whiteboard to draw things for you.
You cannot open a whiteboard during a screen share.
Yeah, and then I can draw with my finger, and that'll definitely make it more clear for you all. It will not, I promise. All right. So all of these things that I'm talking about here, they're all fully tunable, right? Like dlmalloc made its own choices and it kind of hard-coded that stuff in there, and different operating systems make different changes to it. Different versions of libc have made different decisions about it, but everything in JEmalloc from the jump is made to be more tunable, so you can run these profilers over the thing for your program and then come up with the optimal kind of numbers to use for your program, right? So, how granular our chunk sizes are, how many runs we're keeping track of per chunk size, all that stuff is totally changeable while the structure itself of the allocator remains the same. So, what you see in Chrome will be different from what you see in Android, et cetera, et cetera. So the way that structure lays out is the same for all of these heaps. All of that run detail information, that will change. The number of heaps per core will change. no granular, so the way that I laid it out is each chunk is a power of 2. You can have your own granularity for chunk runs. You could say, I want to have 8s, I want to have 16s, I want to have 24s, you know, all that stuff is completely changeable, and you know, looking at different low fragmentation heaps, you'll see different decisions made there. But that structure of metadata someplace else, and all of the chunks in a run are of the same bucket size, that's always the same, right? So what that means is, if you overflow, like thinking about our DL Malloc example, both of those chunks that we allocated were 100 hexabytes, they're the same size, and they were concurrent. In JE Malloc, if those 2 chunks were of different size, say one is 100 and one is 300, they would be in different heaps, and you would not be able to overflow from one into the other. They'd be in totally different runs, right? And so you will always be stuck with the size of the bucket you happen to find yourself in. You know, if you have an overflow from a fixed size object, you can only overflow into other objects of that size, right? Now, in some cases, there are ways to tailor sizes of objects so they fit in buckets properly the way you want them to. We'll look at that a little bit later. Interesting thing here. These allocators are more reliable for exploitation than the inline allocators are, and that is specifically because of this by chunk bucketing, right? Very often, I can pick the size of the chunk that I will be attacking to and from, and if I know the program I'm attacking well, I can pick a bucket size that's really rare for that program. And what that means is there will be less churn on that run. And so what I do to manipulate the heap will be less subject to random garbage that's occurring in the program. Does that make sense, why that would be important? We'll look at that kind of directly, but you would tend to think the more controlled and the more separated an allocator is, the harder it is to exploit, but it's exactly the opposite of that. The more randomness that is there, the less reliability you can get from your exploit, and the more consistency there is in the allocator, the more certain you can be that your exploit will work. You'll get much higher probabilities. Cool? And this is a property that it turns out happens across the board. Anytime you've got more optimization, you have more control and reliability over a program. When you have less optimization and more randomness, you have less ability to control the program. And so if you were looking at any of those information leak bugs that have to do with branch prediction, all of those are a symptom of this. When you perform optimization, you provide control or information to a malicious observer, basically, right? That branch prediction optimizes how the processor runs based on, what is probable and what the data is, right? And so you get a bit of information about timing from that, and that gives you information about what the input data was. Arnav?
Yeah, so I'm a bit confused on what exactly you mean by randomness. Is it like is it just like randomness in like heaps? Is it like pseudo randomness? I'm just a bit confused on the concept.
Okay, so when you are working with heaps, the heap is responsive to what the process is doing and what the users interacting with the process are doing, right? Those users and their interaction are the random element. right? If I want to attack a server and 50 people are trying to connect to a web page, that's one thing. But if I want to attack a server and 500,000 people are trying to connect to a web page on that server, that's a very different thing, right? And I don't know that remotely necessarily. I mean, I could do some timing to try to figure it out. But, you know, I could do that. I could have a time check, time of use bug on myself where I test it and then, something goes on sale and suddenly, you know, what I just tested is not valid anymore, right? So I don't know what the process is necessarily doing in the background. I don't know how many people have connected to it in the past, 30 hours, and that makes a big difference too. All of that are they're not random in terms of like random, provably random, but they're random in terms of like, we don't have the information nor can we get it, right?
And in this case, like optimized, allocators in this case have sort of, I guess as you put, like kind of predictable patterns of behavior because they work one way, just in regards to like despite multiple users interacting with it. So specifically because the runs are separated by size, I can, for example, do something like this. 500,000 people might connect to this website, but when a user connects to the website, the state objects that it makes fall into the buckets of 512, 4096, and 64 bytes. And there are multiple allocations made in all those buckets, but there are no allocations made in the 32-byte bucket. And so I will target my exploit against an object that happens to be 32 bytes, and I will force that to be allocated, knowing that it doesn't matter as much how many people are connected to the website because that bucket will not thrash as much as the other ones. Okay, because that bucket's not being interacted with as much as the other ones. Yeah, just by virtue of how that program happens to be written. Okay. So I need to do that profiling on my own to learn those things, learn which buckets are more or less reliable. But if we were in PT malloc or DL malloc, there's only one bucket, so it doesn't matter if I can pick a 32-byte object at all. It's still going to be consolidating and splitting and thrashing all over the place for all allocations, right? I can't separate what I'm doing from what the rest of the program is doing in any meaningful sense in that scenario, but on a low fragmentation heap scenario, I can pick the bucket size to be most advantageous to me so that randomness does not affect me as much. All right, thank you. Cool. Good question. All right, so how does JE-malloc specifically do this? So there are, each arena is looking at a number of chunk sizes. They're split up in a custom way, but they're handled different based on these thresholds. There's small and medium chunks that fall under a certain page size threshold, and those are part of the runs, and they are always with their bucket size. And then there are separately kind of huge chunks, and those are mmap page backed. They're not within a run themselves, and they are stored globally. So those huge chunk sizes are always subject to trash. Those are not arena-based necessarily, and there's one red-black tree that stores all of those. Okay, so that's important to know when you're looking at, how much randomness to expect when you are attacking objects of certain sizes, right? Or if you want to perform some sort of race condition, it's good to know that these things are all backed by a single tree that's a red-black tree, and so by doing certain allocations and certain orders, you can force a lot of thrash onto that red-black tree, so it's constantly rebalancing itself and kind of back it up with those requests. So for each core, we've got an arena. Each thread has its own arena.
which is its own heap, and you've got an array of fixed size bins, right? Those fixed size bins each have their own size, and each of those bins has multiple runs that are organized in a tree. Each of those runs contains our chunks. Those are the allocations that are returned to the process, right? Those are used or in use or free, right? And then there's a big bitmap for each one of those runs that keeps track of what's in use and what's free in the run. So which chunks are used, which aren't, which can I give out, which can't I, right? And then you've got the huge chunks, which have their big red-black tree. And each huge chunk itself is its own run. It is a contiguous portion of mapped memory, right? But it's its own. So when you free that huge chunk, it's probably going to get released back to the operating system immediately. Okay. So, so how does this differ from what we've seen previously? Now, in both cases, you have to do heap grooming work, and heap grooming work, which was introduced as the technique heap feng shui by Alex Soderov in, I want to say, 2009 Black Hat, which is a great presentation you should take a look at along with the paper that goes with it. I'll link that up in the Canvas. You've got to do that on all heaps. We'll talk about that next class. It's going to be the focus of our next class. It's much easier in this type of heap for the reasons that we just discussed. I know the downside is here, you never have a boilerplate answer. You never have a plug-and-play solution to your problem. On inline allocators, you have a plug-and-play solution, right? Like that, the script that you worked on in the lab with those particular headers, that would work for any bug that you came across that was using dlmalloc, right? Like you could use that solution just like you have a straight up solution for a stack-based buffer overflow. You hit ret, you do the jump ESP, you put your shellcode right after it. That works for every problem of that type. That's not something that you can ever do in a low fragmentation heap, JEmalloc heap style situation. Now that seems like kind of a detriment, and a lot of people, when things moved away from that boilerplate solution, they found themselves unable to do heap exploitation because their reverse engineering skills weren't up to snuff. However, a lot of the people that were doing heap exploitation with that boilerplate solution also had to rely on running their exploits 250 times in order to get them to hit. And at the time, there wasn't so much focus on, let's say, financially motivated actors in exploitation. And so a lot of companies didn't really care quite so much as they do now whether they got hacked. Like, it was a pain in the ass for your IT people and basically nobody else previously. And so almost nobody was looking at logs, and there were no tripwire alert systems that were in high use. And so you could run your exploit 250 times, right? The reason you had to run them 250 times is that you were reliant on luck to see that you had two concurrent chunks, right? AV09 that we looked at, we assume the chunks are concurrent because we're the only, it's a very small program. It only does 2 allocations, and it knows that its libc isn't going to do any more random allocations and freeze in the middle. And so you're basically guaranteed to have those 2 concurrent chunks. Now, if you think about how dlmalloc works, it's kind of obvious that if there's anything in the look-aside lists, then you're not necessarily going to have two allocations, that happen concurrently. They're not going to be concurrent in space necessarily, right? If somebody else has allocated something and freed it, that's on the free list, that's someplace else in memory. And it's not until the free list is exhausted that you're going to get another concurrent allocation, basically, right? So if you wanted to make a reliable DL-malloc exploit in the first place, you still had to be able to reverse engineer enough to understand how to control that heap specifically. But a lot of people didn't bother with that. It was absolutely necessary at the time. Nowadays, it's absolutely necessary. We do not want to crash things. Either you're, using an exploit you wrote yourself, in which case you spent many months working on it. And I think people who are getting into their projects now see how you could spend many months working on a real life exploit. You don't want to burn that. If you are, a professional in this space, you're a professional black hat, you're going to be handing these things over to people that are going to have to use them, and they need to know that it's reliable, or they at least need to know what the probability of reliability is. And so, there's a lot of work to do there to understand how the program works. And in gaining that understanding for the heap manipulation aspect, you're also going to gain an understanding of how the program works just in general for continuation of execution, fixing what you've broken, and all those other things. The upside of this is enormous, though. The allocator can't tell that we've corrupted program data, right? You, as a program writer, almost never validate your own structures, right? I've asked this question for hands several times. Nobody is validating that their own structures have not been corrupted, right? Do you think I wrote that data? There's no bug in there that I'm aware of that I've come up against that can wreck my linked list, and so I trust my linked list data implicitly, right? Now, because glibc is a standard library that's used by everybody, it's worthwhile for them to perform those validation checks, right? Like that's hardening that can be done in a general sense. That's always going to be valid, and they can make those processor trade-offs as security becomes more important to platform's reputation. However, the second you move that metadata out, there's nothing left for the program to validate. So the big brain coders that work on libc can't save you from this problem, right? You have to save yourself from it, and almost no programmer is spending the time to revalidate structures that they themselves built. It doesn't happen, right? So one of the problems with DL-malloc is even if we're attacking the program structures, we're not attacking the metadata. As soon as one of those chunks gets used by the program again in the normal functioning of it, if you haven't gone back and fixed everything you've broken, well, immediately libc knows that corruption has occurred and it will kill the program, right? So that can't happen in this type of situation, right? And then the other upside we've already talked about is that extreme reliability where you get to pick what bucket you're attacking in. You get to pick a lot more about how that program functions because it's so highly optimized. We got a hand up. What's up? Stefan?
So I get that it's the process of attacking the allocator is different. Why can't I write, if I get like a write primitive, why can't I like write to a bitmap to like coerce a double free or something like that?
So a double free is not going to get you anything in this context. And we'll talk about that near the end of this class. First off, that a double free in and of itself is not useful. A double free is just another type of type confusion, right? And what I mean by that is when I'll talk about the double free at the end of class, but basically, in this case, if you double free something, all that happens is the bitmap gets set. That's it, right? And so there's no advantage to doing that. The bitmap was 1, it resets it to 1, that's all there is to it.
If you get, if you were to double free a chunk and then you reallocate one of those chunks, then you write to it, and then another chunk requests one of the same size in it, gives it back that one that's been double freed, don't you now control, you're now controlling something you should be able to control?
You get that without a double free. The fact that a double free occurs means that somebody held on to a pointer that was already freed, and any usage of that is going to give you a use after free.
Right, I'm saying use the bitmap to get that primitive, the use after free. Is that something you can do?
Once you have that right where, if you have a peak that gives you enough information, there are much more direct places to write. And so, if you were married to attacking the allocator for some reason, you could attack the allocator, but it's almost never the advantageous thing to do.
Okay, I see.
Right, once you have that, you have power to do something more useful rather than try to switch it. So you would have to be in a really constrained, strange situation for that to be your next step. Now, I'm not saying that there's never going to be a case where that's not your next best step, but there's probably better ones.
Right, yeah, that makes sense.
Yeah. Yeah, okay, on up.
It's kind of a more general question regarding malloc implementations. Does JE malloc replace DL malloc, or are they just have different use cases?
On many operating systems, this style of heap has replaced it. So on Android in specific, Android only uses JE malloc. BSD only uses JE malloc. Chrome only uses this style of allocator. Firefox only uses this style of allocator, right? Windows uses both styles at different times.
So in the case of Windows, is there, is one allocator just better than another, a specific task, or?
Yeah, so below certain memory usage, DL malloc is more efficient, which is why it was what was written when memory usage was lower. Nowadays, memory usage is much higher. It's less efficient than these low fragmentation heaps. Once you cross that efficiency threshold, and there are academic papers on JE malloc that Jason Evans wrote when he wrote JE malloc, why he made the decisions he did that show where these thresholds are. But yeah, below certain thresholds, one is more efficient. Above certain thresholds, the other one is much, much more efficient. So there's actually, let's talk about real quick one of those reasons why it's more efficient. So let's imagine that you write a linked list, and you write it in, and this is a DL malloc style, and you are walking through the linked list. Now, the linked list is of a fixed object, so it's a single object, which means that all the objects are the same size, but they're all in this linked list. If you're in a highly used DL malloc, they could be all over the place. One's in one page, one's in another page, one's way over here. Okay, now we got to go back to the other page for the fourth one, right? And what that means is that every time you go to your next pointer, your cache has got to page out some pages and page in different pages. And that happens every single time you iterate through this list, right? Every single one causes 5 cache misses on your L3 cache, right? And that's really expensive. Memory on computers is hierarchical, right? You're never reading directly from your RAM stick. Your processor is reading from level 1 cache. Level 1 cache is reading from level 2 cache. Level 2 cache is reading from level 3 cache. Level 3 cache is reading from RAM. And one of the most expensive things when you're buying a processor is how much level 1, level 2, and level 3 cache is there on the processor. That's like the highest speed memory, and that's what registers read from, actually. Beyond that, you're always cache missing, and then performing this juggling act from lower speed memory to higher speed memory. And so one of the things this allocator is meant to do is say, oh, if we put all of the objects of all the same sizes in contiguous pages, then odds are if I page that run in and I go through my linked lists, I'm never going to have a cache miss because they're all going to be in the same run, right? Even if they're not in order, they're still in the same run because of the same size and they're used by the same thread. So I'm not going to have to ask another processor for its cache, et cetera, et cetera, et cetera, right? So that's a huge win and one of the biggest speed bonuses to this allocator, right?
And this is for JEML specifically because it's constantly requesting the same information over and over and over again concurrently, or?
Well, it's not that it's all programs have the same basic structures. This is an optimization for JEML that works for all programs generally, but it's not worth it until the program starts to see a certain amount of thrash in its allocator, right? Like the more Alex and freeze occur, the more the odds are that you're going to have this fragmentation where objects of the same type are far away from each other, right?
I see. All right. I think I better understand. Thank you.
And you know, like I said, the overhead for this is extremely high, right? For every bucket, you have your own run. Now in DLmalloc, if you allocate 8 bytes or you allocate 32 bytes, it just pulls the next thing off the chunk. On JEMalloc, the first time you have a 32 byte allocation, it mmaps several empty pages for that thread, right? And that's the run that's going to service 32-bit requests. And those are lazily done. So your first time, real expensive, and now you've wasted 2 pages of memory. If you never do another 32-byte allocation, you still got 2 pages of memory at least sitting there on your thread. So the overhead is high to gain this benefit, and that's why you look at those thresholds.
I see. Okay, that makes sense.
Okay. Yeah, all right. Let's, anybody else have questions, or shall we get back to it? Okay. Okay, so given that we don't want to attack our allocator, what's actually useful in program structures on the heap generally that we're going to attack? Well, almost everything that lives on the heap is useful for attacking, right? Like any local, if you've got a stack overflow and you don't want to hit the return pointer because you got a canary there for some other reason, just about any local is useful. That stuff is all used to decide how the program works. And your job is to manipulate how the program works, right? So things that we have on the heap in structures and classes, sizes or offsets into structures, useful because if I can set the size or offset into an array or a structure someplace else, like arbitrarily off the end of the thing, I can be reading or writing in memory that's in a totally different object or that's on a totally different memory page, right? State flags are useful, like our fake object in our DLmalloc, or one of our state flags is in use or not, right? You can manipulate your double free if you had one in DLmalloc in this case, right? There's a lot of different things that you can do with state flags. State flags will say, oh, this memory is valid as this type if the state is such and such, right? Like, or say the state is an enum that picks how a union is interpreted. That happens quite often, right? Like, that stuff's useful to overwrite. Any pointer is super useful, right? It can be used as a peek or an arbitrary write, right? Even if it's not pointing at function pointers, if it's just pointing at a next object in a list, and you know where you control some memory and you can point it at your object, you control the next object in that list, right? All that stuff is super useful. V-table pointers are probably the easiest and most direct thing to look at here if you don't have direct function pointers, and V-table pointers are really nice, right? They're a list of function pointers to call. You can make your own, right? That V-table does not necessarily need to point at executable memory. It can point at writable memory because you're not going to execute the V-table, you're going to read pointers on it, and those pointers will be executed, right? So all this stuff is super useful. However, what it means is you need to have a really strong grasp of the program you're attacking. You can't have generic knowledge of the allocator. You have to have specific knowledge of the program you are attacking in the version that you are targeting, right? Which means you have to have done your reverse engineering homework. So you gain more control and less detectability in this situation, but the burden is on you to do the work with the program to understand it in a really deep way. Whoever understands the program controls the program, just like whoever understands the network best controls the network. And this is a great example of that. This is, in hacking history, this is where reverse engineers become king, seriously, right? Because every situation is bespoke. And so every target is you need to do your reverse engineering homework for every single target to be good at it, to make something reliable that you understand. Okay. We've looked at overflows briefly in the DL Malik lab. You understand overflows kind of intuitively after working with our stack stuff. That's the same on the heap, right? You are linearly writing, and the question is, what are you going to hit during your linear write? And what that means is, if you can draw the stack, you understand it. If you can draw the heap and control, where allocations go on the heap, you can figure out that overflow. The use after free is a slightly different paradigm. The use after free says somebody freed something, and it goes back on the free list. However, someone is holding a pointer to that, and they're not aware that it's free. That's the real crux of the thing, is that there is a pointer held to memory that was freed, and the program holding that pointer is not aware that it was free. So a double free is just a use after free, and they are type confusion style memory corruption attacks. And that means that the program, because it is holding a pointer of a certain size, certain type, will interact with that memory as though it is a certain type. Because that memory is freed, it can be given back out again by the allocator to any request of a similar size. It doesn't have to be an exact size, it has to be in that bucket. So let's say we have something in the 128 byte bucket, it's like an 86 byte allocation, but it is from the 128 byte bucket because that's the next roundup for that configuration, right? Any object that we get that will also fall into that bucket may cause the allocator to hand us back that memory that was just free. Now, we may be of a different type. Now, the easiest explanation to give for this, and I would be drawing a lot on the whiteboard now if I could, is that, like, say you ask for a string, you get to decide the length of the string, and you get to decide what goes in the string, and the program's going to allocate some space and copy the string there, right? So I have a use after free. It's an 86 byte use after free, and it's of object type A. The program's holding on to that pointer. It knows it's object type A. It's going to interact with it, and so it's object type A. However, I made a request for a 128 byte string, and I copy it full of A's. Okay? That pointer to object A is now pointing at my string of A's. And now I have full control over everything in that structure. Object A, everything in object A belongs to me. right? I can make arbitrary decisions about what that data is now, and that program will still interact with it as object A. Now, if I am extremely good at this, what I'm going to do is, instead of filling it with A's, I'll fill it with data that's advantageous to me. So if it's a class, a C++ class, and there is a vtable pointer in there, then I will control that vtable pointer, and I will point it at some place that is good for me, either a vtable, a fake vtable that I made, if I know where some memory is that I control, or a different vtable where different functions will be called on the same data, right? If there are pointers in there to other objects, I may point them at other data that I control. I have full access to do all of those things with a use after free, right? And a double free is exactly the same thing. You do a double free, that gives you the opportunity to put those fake chunks in. If you're looking at a double free on DL malloc, which is where a double free is actually useful, that PT malloc, DL malloc style inline data, you can add a fake chunk with the double free, right? You get it back. Now you control the forward and back links. You control any data that's within it, and you can manipulate that allocator with the double free. But it's just another type of use after free. Okay, this works with any type of pointer. Okay, so this is just a walkthrough of exactly how this happens, right? So you free an object, and you don't set the pointer to null for some reason. Or while it's being freed, you set it to null, but somebody else is still maintaining this pointer, like say in a linked list somewhere, right? And there's no way to go back up and say, hey, pull that out of the linked list. Then you have an allocation made of the same size, but a different type. And you've got that kind of last in, first out kind of look-aside list behavior going on. So the thing that was just freed is the thing that's handed back. Same thing, okay? You populate that chunk with new data, and it doesn't even have to be data you fully control. It could be of any other type. You're still going to get memory corruption. And then that old pointer is used, and it assumes the old type, but the data is not of the old type. It is of the new type. And because that data is a type mismatch, corruption can occur there, right? Even if there's no control over that new type, well, I may be calling function pointers that make assumptions about the data that can still be advantageous to me. I can use that to get a peek in a lot of situations, right? Does that make sense? Where are we at on time here? Getting close, okay. The problem here is that in all cases for the heap, we have to have perfect control over these allocations. We need to be able to set up situations where we know we will get access to that next chunk, right? Even if you're looking at more advanced allocator attacks, like you're looking at the look-aside list, singly linked list corruption type of deal. What you're doing there is you're saying, oh, I'm gonna force an arbitrary pointer to be on the look-aside list so that next time I allocate something of that size, it's gonna give me this pointer and I'll be able to write to arbitrary memory with that, right? Well, you need to be goddamn sure that you're the one that's gonna make that next allocation of that size. And so that requires a lot of knowledge and control over the situation. How do you make sure that happens? How do you pick those buckets, right? If you are overflowing in particular, you need to know that your chunk you're overflowing from, the one that's got the bug in it that you're going to manipulate, is going to be right next to something that you can also use, right? If it happens to be abutted against a random chunk or the end of the heap, well, all you're going to get is a crash, right? You're going to corrupt something random that you don't know about. The program's going to use it, it'll crash, or you'll write off the end of the heap. You'll hit the guard page, you'll get a crash immediately right there, right? You need to know how to manipulate that heap in order to say, okay, I'll be the next one to make the allocation. It will be next to my other chunk that I control. No one else will use those objects until I use them, at which point I will gain control of the program and I can fix everything so it won't crash, right? That is, if you are looking at this in abstraction and nobody told you that this was possible, you would think that this is not a thing that you could do reliably. And it was thought that this was not a possible thing to do. And so for many years, people said, oh, if you want to make a secure program, you put your stuff on the heap because no one can exploit the heap. Like, that was a thing people said. To some degree, they turned out to be right, because the number of people who continued on to be exploit developers, once we got to the point where we were looking at this type of manipulation, that number dwindled significantly. Like, the number of people that were capable of hitting those Stack Overflows, infinite. The number of people that cared enough to do the work to be good at these complicated heap manipulations was vanishingly small in comparison. And that's, part of that Dave Vitale total cost of ownership, right? It's more expensive in terms of time and expertise to exploit those bugs. And so fewer people will do it, and so the cost goes up, and so, theoretically the consumer is more protected. However, this is about protecting companies and not consumers, and with the rise of ransomware, that calculation changes rapidly, and of course with espionage and warfare, that those numbers are incalculable, basically, right? So, this stuff is still going to happen. It's still doable, and we will learn how to do it, perform those manipulations in our next class, which hopefully I will be at in person, because I don't want to have to teach that without a whiteboard. So I think that's everything that I wanted to say about JE Malloc. And once again, I apologize for not having, being there in person to walk through it visually with you, because I think it really benefits from the visual. So maybe I'll start next class once I can get there in person with drawing out the structures for JE Malloc, and then we'll work on the manipulation from there. That was a lot of talking. Does anybody have questions? No? All right, cool. Then I guess we can end about 8 minutes early today for undergrad. I'm going to take a break and grab some more water.
Recording stopped.
And we'll do some discussion post-class. And I think what I want to focus on is where people are at on their final projects, and maybe talking through some lessons learned.
Well, I need to stop.
I'm good? All right, I'll be back momentarily.
So I have to do this.